To another episode of the Chemistry Senior Experience Seminars 2022. We are going to be hearing from Elizabeth Liebau today, and I'm going to give her introduction. So Elizabeth joins us from Thiensville, Wisconsin, and she came to Lawrence to be a pre-med major, which she is still planning on continuing. She wants to do pediatric oncology, and she is a double major in biochem and Spanish with a minor in psychology. So she has been busy during her time here in many different departments. And she got interested in the topic she's going to tell you about today when she took Biochemistry 2 with her advisor, Kim Dixon. And she did a presentation on a paper that she read, and she got really interested in chronic inflammation and neurochemical pathways involved in that process. So she's here to tell you about her work that she's been working on all term, and we are excited to hear about it. So take it away, Elizabeth.
All right. So again, my name is Elizabeth Liebau, and I'm a biochemistry and Spanish double major with a minor in psychology here at Lawrence. And so I've kind of deemed this my neurological biochemistry presentation here. So it's going to be a little bit different than some of the more purely chem talks that we've already had, but I'm really excited to share my research. So today I'll be talking about the targeting of regulator of G protein signaling 4, also known as RGS4, for the possible targeting of treatments for chronic pain. So I first want to start off by acknowledging some of the people that helped me get here. So the first person being the lovely Professor Rachel Dowdy, who's really helped me narrow in and hone in on this presentation. My advisor, Kimberly Dixon, for helping me discover this topic through her Biochemistry 2 class and even teaching me about biochemistry, because that is a main focus here. And all my lovely peers in the Chem 680 class who have given me feedback. So a brief outline on what I'm going to talk about today is first I'm going to start off with some relevance and background information. Why should you be sitting here listening to me talking at you for half an hour? Then I'll go into the methodologies for a paper by Rampu et al., and then give you some of their results, and then lead a discussion and some conclusions based on their paper. So before I start telling you why you should be listening, I want to start off by defining a couple key words. So the first word being hyperalgesia, which is an increased pain response to a stimuli. And so this here is really like increased sensitivity to a feeling of pain or like an extreme pain response. So this usually happens like when there's nerve damage or chemical changes to pain pathways. So let's say like your hand's already a little bit sore, you touch it, now all of a sudden it's extremely painful. That would be a hyperalgesic response. Similarly, we have allodynia, which is a non-painful stimulus becomes painful. So let's say you touch your arm. That should not be painful, but now all of a sudden it's really hypersensitive, so that is what an allodynic response is. We have agonist, which is a substance that involves like a response when it's paired to a receptor. So when something binds, that agonist starts this cascade of signaling events. And lastly, a negative modulator, when really referring to allosteric reactions, is when the binding of one molecule decreases the affinity for another to bind. So some relevance. So when talking about pain, especially in chronic and acute pain, I need to really start off by defining what these terms are and how I will be using them here. So the time frame. So acute pain does not last very long. It has a known mechanism, and it has like a known okay, you will be recovering from this for maybe 1 to 2 weeks. That is a normal pain reaction. However, on the other hand, we have chronic pain, which then outlasts that normal pain response. So it kind of just keeps going when you should not be feeling any pain. So acute pain is evolutionarily favorable, and you might be wondering why pain could be favorable. So let's say you accidentally touch a hot stove. You will then quickly jerk your hand away. That is because your brain is telling you, that's hot. I do not want to cause any nerve or pain damage, so I'm going to stop that reaction. So that pain response is what stops you from causing further damage. Whereas chronic pain, there's really no evolutionary purpose. There's no reason why somebody should be in pain consistently all the time. So once acute pain goes away, you can return to your normal baseline function, whatever it is you were doing before. But however, when it comes to chronic pain, it can lead to long-term and lasting nerve damage. So you never will really be able to get that same level of function back, which is why chronic pain is so serious. And so Some other symptoms with chronic pain that are especially important to recognize is anxiety and depression. And that makes sense really for two reasons. The first being that the areas of the brain which are used for encoding pain and for anxiety and depression and those types of thoughts and feelings are kind of right by each other. So when one is off, it's really easy for signaling then to differ when going across both brain regions. It also makes sense too, because if you're constantly in pain, it can lead to this really negative cycle of bad thoughts and feelings, which can then lead to anxiety and depression. Acute pain, on the other hand, once you have healed, you might have a scar, you might have a burn mark, but that all fades with time. And so some examples, some of which I've already kind of mentioned for acute pain, you have surgery, burns, bone fractures, everything that will kind of heal and go away, but will cause some pain for a little while. And then for chronic pain, we have the neuropathic pain, so any type of nerve pain, migraines, arthritis, fibromyalgia, and things like that. So some interesting and kind of sad statistics is that, first off, it's estimated that more than 25 million adults in the US alone suffer from chronic pain. So this chart here is from the Center for Disease Control, the CDC. And so we see in green, we have women who are showing higher rates of prevalency of chronic pain when compared with men in the orangey gold color. So for chronic pain, we see women at about 21.7% and men at about 19%. This here then contrasts with high impact chronic pain. And really that difference there when looking at high impact chronic pain is that it really disrupts all daily functions. So your ability to do school, to work, to eat, to sleep, to do things that you should normally be able to do in your daily life. And again, here we see women with a slightly higher prevalency rate than compared with men, women at about 8.5% and men at 6.3%. This same study then looked at race as well. And so we see in navy blue, we see non-Hispanic whites, in gold, the non-Hispanic blacks, in green, Hispanics, and in pink, non-Hispanic Asians. So we are seeing with these charts, again, from the CDC, that the non-Hispanic whites are showing a higher prevalency rate compared with non-Hispanic blacks, Hispanics, and non-Hispanic Asians. Though one thing I do want to mention when looking at both of these charts side by side is that there's still a lot of stigma out there. And so when looking at these recordings from the CDC, looking at diagnosed chronic pain across different cultures, races, genders, identities, there's very different willingness and acceptance of seeking medical professionals. So this here is still very important data that shows current trends, but it does not account for all people who are suffering with chronic pain. And to also just kind of conceptualize that, the CDC does estimate that about 21% of US adults have reported having chronic pain. So where does chronic pain happen? So we see chronic pain taking place in the pain matrix. And so that is referring to the parts of your brain that mediate nociception, mood, and motivation, and most commonly called your central nervous system. So your central nervous system is referring mostly to your brain and your spinal cord, where all of these messages are being encoded. One key part of the brain that I would like to mention is the thalamus, and that is mostly where we see the encoding for chronic pain and just pain signals and sensory signals in general. So when this gets off, this is where we can see higher levels of RGS4, which I will be explaining shortly. Okay, so I'm talking about these really high prevalency rates for chronic pain, and you might be wondering, what are we doing about that right now? Don't we have treatments? Don't we have cures? Don't we have something out there? And right now, our most common treatment for chronic pain and acute pain both are opioids. So some common examples that you might have heard of before might be Vicodin, oxycodone, fentanyl, heroin, all those types of drugs that are derived from the poppy plant. And so they are widely used for treating acute and chronic pain, and their uses date back to the 7th century from the Chinese Empire. Though they have one tiny little problem, is that long-term use can lead to tolerance and addiction. And so this high rate of addiction is what we now call the opioid crisis. So in 2016, it was estimated that about 42,000 opioid-related deaths. There were 42,000 opioid-related deaths in the USA alone. And then in 2019, this number jumped to about 50,000 opioid-related deaths in the US. And of all accidental and drug overdoses, opioids are responsible for about 21% of them. So this graphic here is from the CDC, and so this dark green color that we're seeing represents the highest category of 21.1 to 57 deaths per 100,000 for opioid-related deaths. And we see where we are right here in Wisconsin has that dark green color. Wisconsin in 2019 had 21.1 opioid-related deaths per 100,000. So we are in the high end of this, and that is not something that we want to see. So finding a better solution than using opioids to treat pain is really important. So you've heard me say RGS4 a couple of times, and you might be wondering, what does that mean? So RGS4 is a regulator of G protein signaling 4. So I'm going to start breaking down that word by starting off with G proteins. So G proteins are the largest class of cell surface receptors, meaning that they're really just kind of found like on that cell wall, cell membrane, and do a lot of binding actions. They are currently very popular therapeutic targets for cardiovascular disease, cancer, and asthma, and that is because they bind neurotransmitters, hormones, growth factors, ligands, and RGS proteins. And so their ability to bind neurotransmitters and hormones, which are primarily responsible for these sensations, is really important as to why they are a great area to target when looking at finding treatments for acute and both chronic pain. So breaking down RGS4 a little bit further, we have RGS, and RGS refers to the regulator of G protein signaling. So these RGS proteins, they are negative regulators of signaling binding proteins. So once they bind, nothing else can bind. And so they are biased agonists of the mu-opioid receptor. The mu-opioid receptor is one of 3 opioid receptors found in your nervous system. You have your mu, your kappa, and your delta opioid receptors, and the mu is one that's most commonly targeted when looking at pain, but you do have the other 2 as well. And so they are cytoplasmic proteins that facilitate GTPase activity for G proteins. And so GTPase is an enzyme that breaks down GTP, which is an energy molecule. So this diagram here shows an opioid receptor and the RGS4 binding to it. So there's a lot of different parts of the binding process. And so I just want to break them down even a little bit further, because this is where I had to spend the most time really looking into what is RGS, what's RGS4, how do these all kind of come together. So there are 20 different RGS proteins so these RGS proteins then bind to G proteins. And so currently we have RGS4 and RGS9, which are being used and studied right now for targeting the mu-opioid receptor. So this diagram here I really love. I found it on the internet, and it was super amazing for being able to kind of simplify and break down this binding process, because I feel like up until this point, I have just been saying this, it keeps binding to this, which binds to this, which in my opinion gets a little bit confusing. So this here shows your GPCR, which is your G protein coupled receptor, which then binds this RGS box, which is showing this RGS protein. And so the RGS protein then also has alpha helix structure, which we will see on some of the following slides. And there are noted for the N-terminal alternating pattern. That is not important for my talk, but for the chemist here, I figured I would mention. So it then comes in and it binds to those G protein coupled receptors. So finally, my protein, RGS4. So RGS4 is a signal transduction protein that modulates G protein receptors that controls the function of monoamine, opioid, and other G proteins that are found throughout the entire pain matrix. So that's a mouthful. So we're going to break that down a little bit. So it's a signal transduction protein that modulates G protein receptors. So it is a protein that when it binds, it starts this whole cascade of further reactions. And so it controls your monoamines, opioids, and other G proteins that are then found throughout that pain matrix, that central nervous system. So it is a 28 kilodalton protein. And if you are like me and you do not think of things in the weights of kilodaltons, I converted that to pounds. And that comes out to be about 1.025 times 10 to the minus 22nd pounds. Meaning it's really small, it's really light, which then explains why it can be found everywhere in that pain matrix. And it's also been found to modulate responses to psychostimulants and antidepressants. So it's also known to not just have an effect with pain, but also for depression and anxiety as well. And that's another common target as well. So I talked a little bit about opioids, and so we're going to kind of wrap this kind of all up together and explain now why this RGS4 and these opioid receptors and pain makes perfect sense. So it is an opioid receptor agonist, mostly for the mu-opioid receptor. And so it's a negative modulator of opioid reward, and it promotes analgesic actions on certain opioid agonists. So really when it binds to your opioid receptors, and you can kind of just see your typical synaptic cleft where you have binding proteins, when it binds, it then changes the sensations that you are feeling. And so what is being found is that the knockout of RGS4 reduces the responses to fentanyl and methadone, but not to morphine. And so that's really interesting and very important because let's say we're able to knock out RGS4 or create medications that do that one day down the road. And if you end up in hospital needing some type of pain medication for a procedure or anything else like that, knowing that morphine is still able to act as a pain medication is really important when looking at this long-term big picture. So before kind of moving on to my methodologies, I just kind of want to summarize again why this is important and why you should keep listening to me ramble on about RGS4. So we already know it plays a role in mitigating chronic pain, and that it's an effective pain treatment targeting could lead to finding alternatives for highly addictive opioid therapies and actually possibly be a success in treating chronic pain, which is something we've had very little success with up until this point. So the purpose of the research that I will be explaining is to better understand the role and mechanisms of RGS4 and its role in the pain matrix. Okay, so for my methodologies, I will be focusing on a paper by Rompu et al., which came out in 2019. And so a little bit of background on how this started and how it kind of works is in order to compare mice with and without this RGS4 protein, they created this RGS4 wild type and the RGS4 knockout mice. And something I think is really important and really cool to mention is that they use both male and female mice. Now, that might kind of seem like a no-brainer that you want mice of both male and female, but this here is very much a neuroscience paper as well as being biochemistry. And very commonly in neuroscience, we find that female mice, rodents, animals are not used due to the added complexities of female reproduction, menstruation, and just the female bodies and trying to get rid of any other factors. So this paper does do a little bit of comparison, but the graphs and figures I will be showing use both male and female mice. So this first section of methodologies, we'll be working with the complete forage adjuvant, which is also called CFA, and what I will be calling it because saying complete forage adjuvant a lot of times is very difficult. And so on the bottom left, we have a photo of the chemical compound for CFA. It really is its own chemical compound. And so what they did was they combined it with a 1-to-1 ratio with saline and injected it into the left hind paw of the mice. And this purpose here is to mimic chronic pain by causing swelling in that paw. So after injecting the CFA, they did 3 separate methods that I'm going to be talking about. The first one being voluntary wheel running, which is kind of exactly what it sounds like. So they did a baseline measurement and then a 13-day post-CFA measurement where the amount of time that the mice spent running on the wheel willingly was then measured and compared. And so basically what it's trying to say is if their paw is in pain, they're not going to be wanting to run as much as when they are not in pain. So that's a really great way to test, are the mice still in pain, or are they not? And looking at both the knockout and wild-type mice. The second test involving the CFA is the cold plate test. And this here is also very much what it sounds like. So it's to test the cold allodynia response. And so the cold plate was set to 0 degrees Celsius or 32 degrees Fahrenheit. And as we all know, living in Wisconsin, 32 degrees Fahrenheit, it's cold, it's freezing temperature, it's uncomfortable, but for a short-term exposure, it's not going to cause a long-term damage, which is why it's a great way to test if the cold is bugging that paw that was injected with that CFA. And the third methodology involving that CFA is a Voluntary assay. And so what is done here is the left hind paw, which was injected with that CFA, was then poked with this sharp needle. And when I say sharp, it's not meant to like pierce through their paw. It's just kind of uncomfortable, like if they start kind of just poking at you with like a sewing needle. It's not going to go right through your skin, but it's not also a very comfortable feeling as well. And so this here is measured at different pressures to then see at what pressure point they are flinching their paw away and showing pain. So this here was analyzed 17 days post-CFA. And again, this here is a test at neuropathic pain response. So for the results for the wheel running, on the y-axis we have the percent of native wild-type baseline. And so that 100 mark is basically kind of our one, that's our basis of measurement. So where we see that black with the wild-type mice, that's kind of where we are comparing from. So if it increased, that means that there was more running, and if it decreased, so that was showing less running. And so then we see the baseline for both our wild-type and knockout mice. For our wild-type mice, we see about a 50% decrease from their baseline measurement. This 50% decrease does show that they were still in pain because they were not running at the same levels that they were prior to the injection. However, what is super interesting is that the knockout mice, 13 days post-CFA, were running at the same levels as to prior the injection. So this same level of wheel running shows recovery from the chronic pain states. For our cold plate test, the baselines were even for both the wild type and knockout mice, so that was not included. And so it shows a flinching latency in seconds on our y-axis. And that flinching latency is how long they can be on that cold plate before they start pulling away that CFA-injected paw because it's uncomfortable. So we see for the wild-type mice that they were flinching at about 10 seconds, whereas our knockout mice started flinching around 25 to 30 seconds, showing a really large difference in that flinching behavior because of the cold. So we see that the knockout mice show a reduced flinching latency, demonstrating a reduced pain response when compared with the wild-type mice, again showing that recovery. And then for our Voluntary assay, we have a slightly different chart here, and so we have the Voluntary response in grams. So that's how much pressure they're able to apply before you get this like flinching behavior, showing the pain. So we have our baseline at about 1.3, 1.4 grams of pressure. At day 3, we see very similar results for the wild-type and knockout mice. But then from day 9 through day 17, we start to see a recovery in the knockout mice in the light gray color up here. And the dark line shows the wild-type mice, and we see that they are staying at the same level of pain response between 3 and 17 days post-CFA. So this here shows that by 17 days, the wild-type mice have not recovered from the pain response, but our knockout mice are showing a trend towards that baseline measurement. So there's one other test and methodology I do want to touch on because it shows the fact that RGS4 does not impact acute pain. And as I mentioned earlier, acute pain is very important evolutionarily to protect ourselves from causing catastrophic damage. So in order to do this, they use a formalin test. So this test works very similar to the CFA injection, where that left hind paw, and these are different mice than the CFA mice, were injected with a 4% formaldehyde solution. Some of us might be familiar with formaldehyde. It would be a little bit uncomfortable, but it's not supposed to cause any damage to the mice, besides create this acute pain response. So then their behaviors were measured for an hour after their injection, and their licking and flinching behaviors were then recorded by double-blind researchers. And so the results from this show on the y-axis the nociceptive score, and so the higher score shows recovery from nociception, whereas the lower score shows that they are still feeling more pain. I said that backwards. So the higher score shows that they are showing more pain responses, whereas the lower score is showing that they are participating in less pain behaviors. So in the dark color, again, we have the wild-type mice where they are kind of neck and neck, showing the same amount of licking and flinching behaviors for the first 40 minutes. But then after the first 40 minutes, we start to see the knockout mice having a lower nociceptive score, so again, showing less pain behaviors, and we're kind of recovering, whereas the wild-type mice are still showing a pain response at 40 and 60 minutes. And this here shows that those first 40 minutes are showing that the knockout mice are still feeling this acute pain. They are still responding accordingly to having this formaldehyde injection, but they are recovering faster compared with their wild-type counterparts. So, some discussions and conclusions. So, what do we know? We know that RGS4 does play a role in chronic pain, and especially when maintaining cold and mechanical allodynia, and that RGS4 does not affect acute pain responses. So this is important. This is big. This is showing that we have a molecule here that, if we can properly target it, does not affect acute pain responses, which is what we want, but that when we knock it out, we're not feeling and seeing these same chronic pain responses. Could be a really positive and beneficial target to creating treatments to help that 25 million Americans and people worldwide struggling with chronic pain. So a few proposed next steps is reassessing these models. This Avrampu paper does kind of coincide with other papers I have read and seen, but this one really does clearly test for so many different neurological effects inside and showing the processes of RGS4, which is why I decided to focus on it. But we do need to see this in more rodent and non-human primate models to see, are we getting the same results? Also then possibly working to synthesize a medication to inhibit that RGS4 pathway, and then also being able to fund these studies. Studies like this is not cheap, so being able to get funding to keep reassessing and synthesizing medications to do this would be super beneficial. So some lasting conclusions I do want to leave with you is that, as much as I make it sound like it's going to be so easy to synthesize some medication that can knock out RGS4, that is far from true. All the chemists in the room talking about all their retroactive synthesis processes to try and create a molecule that they think might work is super complex, takes a lot of time, and RGS4 is so abundant in your central nervous system in that pain matrix that then coming up with a molecule that can first either knock it out or even knock it out in certain brain regions is far from easy. But if it's something that can be done, could lead to a lot of people not suffering the same amount of pain that they have been going through for months, years, decades, whatever it is. This RGS4 protein and other RGS proteins could be a key in curing and treating these chronic pain successfully and without all the extra side effects of opioids, which is why we really are looking down these paths. And lastly, we do need to study this in non-human primates and other rodents to assess for neurocognitive behaviors. And I say that because when making any type of medication, especially one that is going to target your brain, we want to make sure that the good it's doing outweighs any possible side effects. So a different paper by Chernitzky et al. Did measure this in a rodent model, and they saw that there were no difference in neurocognitive behaviors between the knockout mice and the wild-type mice. But to keep reassessing and seeing if these are the same trends is very important before taking this any further as well. So here are some of my citations, sources, and I'm open to questions as well. So thank you.
All right, thank you, Elizabeth. And we're now open for questions. You can raise your hand, or I'll watch on Zoom if anyone wants to ask one there. Yes, Adriana.
You mentioned that it does not work on morphine, which is a positive thing, but do you happen to know what the reasoning is or what the mechanism is that morphine behaves differently?
Yes, that's a great question. So we have the 3 different opioid receptors. We have our mu, our kappa, and our delta. And so morphine works on more than just your mu opioid receptor, which is the most common target with opioids and especially RGS4. So we know that morphine does work on your kappa and your delta opioid receptors. So it being able to bind to those other opioid receptors is most likely the reason that it still works in these knockout models.
Thank you.
Yeah, Eder.
My question is, do you know how long it will take for it to be tested on humans or for it to go through human trials?
I do not know what the time frame is right now to get it that far. I know that there's definitely going to be, they're going to need to do a lot more rodent models. I don't know even if it's feasible to make a knockout in a non-human primate, and to get any permits to work with non-human primates is extremely difficult. So I don't know if that would even be able to happen until after synthesis of either like a treatment like that can do that, or a synthesis of a medication would be able to happen. So I would say it's probably many years away, but it's not impossible. Yes.
Jesse.
Earlier on, you mentioned kilodaltons as a unit, and I'm also not very familiar with daltons. So, like, just for reference, like, what would be something that weighs 1 dalton?
That's a great question that I cannot answer. The paper that I worked with decided to explain its size in kilodaltons, and I went, I don't know what that means. So I put it into pounds to better conceptualize it myself. But I'm guessing that probably like a small molecule. Stefan.
This is grams per mole.
Just some
It's grams per mole.
grams per mole.
So one hydrogen atom would be 1 dalton.
There we go.
Cool.
I think I saw Glorielli's hand. Yeah.
Yes, so when you were talking about the experiment with the mice, and you said that they had to, were they injecting CFA?
Yes.
Yes, okay. So then, my question is, what is the significance of CFA? I might have missed it. Does it make the mice more sensitive, or is it actually causing them pain?
Yeah, so CFA induces a swelling response in that paw, and so it lasts for over multiple days. So it's a way to measure a chronic pain state, because it creates that like swelling and inflammation and more sensitivity to pain in that paw where it's injected. So that's really the purpose, is just to mimic chronic pain.
Other questions for the speaker? Yeah, Carmen.
I have a question, but it's more related to like the ethics of using data. So if you don't know it for sure, no worries. But I was just curious, on the first chart you had with the statistics of chronic pain, and you had mentioned the discrimination that we see a lot of times in healthcare. Do you think that discrimination is enough to say that data is inaccurate and we can't use that data?
So are you talking about like with female mice normally being not used in neurological studies?
No, sorry. It was like way at the beginning where we had like the non-Hispanic whites. And
Oh, okay.
Yeah.
I don't know if it's really it's hard to say for sure whether it is a thing of ethics and minorities coming in and not being able to get the diagnoses that they need, or if it's more of a cultural stigma or some type of stigma like that. It could be a little bit both, playing in, or even just access to healthcare. It's really hard to pinpoint one reason as to why that could be, and that's very much possible to be part of the reasoning why we do see the more minorities showing less prevalency rates. But without knowing how the CDC did completely conduct it, it's hard to say.
All right, if that's all our questions. Wait, we have one more question for
One more.
Mike.
Can I pull you back to the graph you had with the exercise wheel and the time that they spent on that?
Yes, if I can get rid of this laser pointer.
Sorry, hopefully you can find it quick.
Okay, I got a mouse. Oh no, what did I do? Oh no. I've hit buttons. I do not know what they do. Okay.
Yeah, what I saw there is the reason to develop another performance-enhancing drug. Okay, look at that.
That's,
You run that much longer than baseline if you can knock it out.
I mean, that's a very interesting way to look at it, because I hadn't even thought about that in like with professional athletes and how it could be a way to help them recover faster, or at least not feel those pain responses when recovering. But I think this model more so does show that chronic pain response. So I think it would be like when looking at this in a human model, it would not be 13 days. It would be like over a much longer time frame.
Well, even on the baseline, okay, at the start.
Whether that baseline stays consistently like that or not.
Yeah.
Probably not.
Most likely, I think it just could be like the mice that were taken from that sample, because they're all 2 to 3 month old mice. So it could just be you had some really high energy mice that randomly got assigned to one group versus the other group that was maybe a little bit more less energized compared. So it could just be with the mice. Whether it is a knockout or not, it's hard to say just from this study. Yeah.
Thank you.
Any other questions? All right. If no, let's thank our speaker again. So our next speaker is going to be Eder, and he'll be starting at 4 o'clock. So have a snack, talk to your neighbor, and we'll be back in 15.
I'm not sure.